All right. So typically, I was going to answer three questions: who we are, why we're doing this course, and who this is for. So just generally, we started. I come from a college in Mumbai called DJ Sanghvi College of Engineering, and back in college, I wanted to do a lot of things, but opportunities were a bit few and far between, and it was a bit hard to get the right things lined up to teach me exactly what I wanted to learn. So we started a club called Unicode, which essentially coached students on doing open source software development. It was modeled after a bunch of other societies. I think IIT Kanpur had one. Lots of other institutes had different societies, but just to give you an example, we had seniors mentoring juniors, juniors mentoring sophomores, or Ts mentoring SEs, BEs mentoring TEs, as the case may be. And it seemed to work out reasonably well. And so we did software development for a year, 2 years, 3 years. Eventually, I got into a PhD program and I was like, okay, well, research could be done in the same way. And so we started the statistics reading group. And then I coached a couple of students, or they coached me, in studying statistics and advanced statistics at the time. And then we discussed, okay, this is a good foundation for machine learning. And so we launched this course just hoping to give more people the opportunity to learn machine learning in a distributed sense, which means you learn from a bunch of other people, from a bunch of online resources. Just because doing self study and reading a book by yourself is much harder than it seems to be. Even if you have a course available online, the videos are up. It's just, at least for me, I find it really hard to sit and watch these videos without having anyone alongside studying the same thing to discuss things with, just to feel like you're on the same page and have some doubt discussions, build some cool stuff that applies these concepts that we're learning. So that is essentially the idea of the course. Another important part of what this course is about is also to sort of stimulate this focus on research. By which I mean you start by reading research papers, but you also want to do a bit of research. And it's, again, really hard to pick the right first problem, in the sense that it should be a bite sized problem just to give you the confidence to pick on bigger problems right after that. Which is, again, why we focus on a course project more than homework assignments. And, we have these readings, but we're not really going to sit and grade your reading in the sense that, oh, you mentioned something wrong about it. The readings are more to ensure we know that you read what you were supposed to read, just so you have enough context for the lecture. So anyway, that's who we are and why we're doing this course. Who this course is for the average Indian undergrad who wants to do machine learning, might not have the perfect set of opportunities to learn from, and might not have a great set of people to learn alongside. So we just decided to open this up to a bunch of more people than we originally planned to. All of my TAs are volunteers. They have been working and will continue to work alongside me for a while. They're really, really nice people. So feel free to reach out to them. If you have any questions, feel free to reach out to me if you have any questions about the course, about machine learning in general. And as a rule of thumb, you are free to raise your hand at any point in the lecture, post a chat. I would prefer you don't unmute yourself directly, although I've left that permission up to you. If you really have a burning question, then sure, go ahead. Just don't interrupt the flow of the class. That is all I ask. So if I'm switching slides, that's a good point to pause and say, can I ask a question? But yeah, in general, it's relatively free form. We've tried to do everything we can to ensure you guys have a formal structure to things, and we will continue to update our understanding of how a course should be, because we are all also first time teachers and TAs. We've fashioned the course after a lot of, well, since the audience is largely Indian, well, there is a certain style of course that the course structure that is followed abroad, which seems to be at least in the US and Europe that I know of, which seem to be a reasonable way to approach things, in the sense you divide the course into recitations and lectures, and then office hours. So as similar to probably your labs and your lectures back at home. So the recitations will primarily be focused on practical stuff, including coding, tutorials, notebooks, all of those things. The lectures will mainly be focused on this theoretical stuff, but we will discuss applied problems during the lectures, although there will be no coding aspect for the most part. Finally, the office hours are supposed to be unstructured, unrecorded discussions where you can throw your questions at me, myself, and the TAs, and we either answer or quite a few times we will tell you we don't know the right answer, and then we will find the right answer and get back to you. So one key aspect of this you need to understand is also that we are not machine learning experts. That being said, most of us have studied machine learning for a fair bit of time, so at least we can give you good intuition on how to look for answers. And of course, we will also give you the answers eventually. But that's the key idea here, that we're all learning together, and hopefully that suffices to give you a good head start in machine learning. So with that said, let me get into course logistics first. Let me know if you can see my screen. I think a yes in chat would be great. And I have lost the chat. I know how my professors felt now. I see chat now. Cool. I see many yeses. So I'm going to assume we're good to go. So really quickly, let's go course logistics. So the course is about an introduction to deep learning. However, I call it a machine learning course mainly because these are things you are going to find commonly applied in machine learning. We are going to discuss problems that are applications of machine learning and not just deep learning. We're going to discuss a lot of foundations that are common to both machine learning and deep learning. And in general, to my understanding, deep learning is a subfield within machine learning. So the application of deep neural.
Only the taskbar is visible. You might want to.
Oh, okay.
Yeah.
You said only the taskbar is visible.
Yeah, I'm not sure why that was. I think only a portion of your screen was.
Ah,
Right now it's visible.
okay.
Yeah.
Gotcha. Thank you so much for that. Cool. So screen looks good now. Back to logistics. So the course is about an introduction to deep learning. I've been over sort of the subtle differences between machine learning and deep learning. There will be a bunch of theory, and the upshot is after all that theory, immediately you will do all of the recitations which apply all of those theories. So there won't, for the most part, be theory that you won't have an application in mind for, which typically helps me learn. I don't know about how in the general, what the general sentiment is about this, but yeah, that's what I'm going to say. The recitations will typically involve Jupyter notebooks. We will be using PyTorch for the duration of this course. And we will solve, or at least attempt to solve, realistic problems that you will actually come across in when you go out to work on machine learning projects. Finally, a bit about the course project. It is designed to allow you to meet other people. It's a virtual setting, and it's super hard to get a community together completely virtually. But we're still going to do our best, and we're going to, I mean, everyone is doing their best these days in COVID. Um, so that's going to be our effort. But the goal of the project is to build a nice, neat, tiny project that is achievable in the 8 week duration, especially given that a lot of you are beginners and don't have significant machine learning experience. So we don't want that to be an impediment, for which reason we will chalk out projects with you that are suited to your skill set. That being said, let's quickly go the course logistics. The lecture schedules will be Saturdays and Sundays, 6 to 8 p.m. Indian Standard Time, which is 8:30 a.m. to 10:30 a.m. Eastern Time for those of you on the Eastern Seaboard. The slides and notebooks are all online. All of the most of the courses based on this. All of the courses based primarily on Alex Mola and team's dive into deep learning textbook. I will have some edits to the slides here and there, which will be released right after the lecture. If it's more convenient, I can also release the slides right before the lecture or a day in advance, although that requires a lot of discipline on my part. CampusFire is just a portal meant for announcements, doubts, discussions. I believe they also have a chat there, but I haven't explored that. I would encourage you to if you like. Discord is more of the community that will last beyond the duration of the course. So we've kept that as a discussion forum and also informal chat, but we would strongly recommend you review the code of conduct on the course website. We don't want untoward incidents to be happening, and we want everyone to be respectful and polite to each other. Yeah, I'm the lecturer. So office hours, like I said before, there are lectures, there are recitation, and then there are office hours, which are typically for unstructured discussions, questions you have about any of the course lecture, recitation, or just machine learning that you want us to discuss. They are also meant for project discussions if you so like, but we will typically take project discussions towards the end of the office hours and take questions about machine learning towards the beginning, just because they're applicable to a broader set of people. So if you're requesting a project discussion during an office hours, might be wise to email us beforehand so we know to keep time for you in the end. Cool. We already spoke of CampusFire. My TAs are Ananya Malik, Aryan Chauhan, Deep Gandhi, Fenil Doshi, Jash Mehta, Jaygala, all of whom are either senior or undergrads or BEs, TEs, and graduate students in the United States. Bs and Ts in India, graduate students in the United States. So they've also been through the whole, or at least are going through the whole applying to grad school grind. So that might be worth asking them about if there is time and if they're willing to talk about that, for those of you interested in those kinds of things. Yeah, generally, just as a side note, Unicode was meant as a student community, not just a coding community and not just machine learning. So yeah, it's supposed to be helping you holistically. If I miss something in chat, please let me know. I'll let the TAs interrupt me. Cool. So we will have a midterm exam. At least the plan is right now to have a midterm exam. It will be 24 hours. You have open access to resources. And we will also try to give you a sample midterm 1 week in advance of the midterm. The sample midterm will probably be composed of questions from midterms from other courses, because it's a lot of effort to ask the TAs to come up with an original sample midterm and the original midterm, which I will obviously also help with. Yeah, the goal of this midterm is just to get you a little more used to like formally taking a course and have accountability more than anything else. The project, cool. We want to have you perform some original work in machine learning. That could be one of either applying known algorithms to new problems, um, which might just include a new data set, or you might create a novel tool by itself. You might have some theoretical contributions and algorithmic analysis of existing algorithms, like clustering in different settings, different kinds of clustering on the same new problem. Anyway, that there are n number of things you can do. We are very flexible on the project. All we ask is that you tell us beforehand so we can chalk out something that is reasonable to accomplish in the time duration you're proposing. And I know this because I have done this myself and I continue to do this myself. I overestimate my abilities and propose projects that take much longer than I initially planned to, which is fine, but just we won't be available beyond the duration of the course to evaluate that project. So it's nicer if you can get it done within the time period. Also, for some of you who are talking about certificates about the course, well, I mean, I've been through the whole process. My TAs have been through the whole process for whatever you want to do in life. Certificates are almost useless. And that's an opinionated statement to make, but I think it comes from a place of experience. I'm going to not take that back. So yeah, what's a lot more useful is the project you will define, build, and the report you will create. Just the experience you get out of that and the way you present that as part of your skill set, as part of your interviews. The whole process of exploratory data analysis, visualizing what your data is, using a learning algorithm, using a certain method, and your evaluations, that is way more important than any certificate anyone would give you. And if you still want a certificate, write to me. I will use an automatic certificate generator online and give it to you, and whatever that means to you, I hope you will be happy with that. But I'm just telling you what I'm going to do if you ask me for a certificate. So yeah, full transparency. So yeah, we have deliverables with schedules and deadlines so that you are accountable to this. The end result of every project should ideally be either a paper or a report, or when I say presentation, I really mean like a paper. I shouldn't have added that here. But yeah, we have a template here. I'll release the slide so you can see this. It is in LaTeX, which is a tool you can use to create these pretty scientific papers. It is annoying to learn, but at some point in your life, if you stay in the field, if you ever write a paper or present an industry, you're going to have to use LaTeX. So we're just trying to get you started early. If you have a serious issue with LaTeX, write to us, but hopefully after you have tried out LaTeX. Just write to us and we'll work something out. But ideally, we would want everyone to at least have a 6 to 8 page paper in this template generated using this platform called Overleaf. I mean, the link is to an Overleaf, so you'll know what Overleaf is. But anyway, more on that later. Some timelines to keep in mind. Ideally, by July 1, you want to register your team with us. We will share the Google Forms that you will use to submit this. By July 10th, preferably much earlier, you would have wanted to talk to course staff at least once about the proposal, about the direction you want to take your project in. By July 15th, there will be a 1 or 2 page at the most project proposal due, including references. There will be a, I would say, 5 minute informal talk where you're just going to talk about like what you want to do in order to get more feedback from the rest of the class. So we'll schedule a session for that. Ideally by August 15th or whenever the course ends, because it's supposed to be 8 weeks, but we might extend it to 10 depending on how you guys all feel about it. And so August 15th or at the end of the course, your final presentation and the report is due, which is 6 to 8 pages at the most, 5 slide, which should be a 5 to 7 minute talk. Again, this is kept mainly for accountability and to train you on how to go about a research project in an end-to-end fashion. At any point, regardless of timelines, talk to us. It is our job to help you chalk this out and finish this. Start early rather than late. Come up to us after having thought about an idea, though. If you're going to come up to us and start pitching several different ideas in very different directions, firstly, we won't have the bandwidth to advise you on all of those ideas. We will ideally just pick one and tell you about that idea, but you will miss out on thinking about the rest. So start early, but like spend time doing your own research. I will link to a Stack Overflow document about how to ask good questions, which is super important, which I found at least highly relevant in my own life. We don't want you to do the project alone. The entire goal of that is to do teamwork. I understand that it's super hard to build a team virtually and actually do all of the work, but on the other hand, everyone else is also going to be looking for a team. So you're in the same boat and that should make life easier. Cool. Ideally, just the three main things you want to do in order of priority: have fun, build stuff, and then learn some skills. I put learn skills as last because that's not measurable. Having fun is measurable. You will realize when you're happy. Building stuff is also measurable. You have some output. Learning skills, it's great, but if anyone ever asks you, they'll ideally want to see how those skills have been applied. So building stuff, in my view, is more important. But either way, that's just an opinion. With that said, I will pause for a minute just in case there are questions. I don't think there are any in chat, but if anyone wants to unmute and ask a question, that should be fine. If ideally try to raise your hand so I can see, or the TAs can see. All right. I don't see any raised hands, but I will mention one important thing that I missed out. There was,
Swapnil,
yeah,
somebody has a question. Gaurang has a question.
cool.
Yeah, so this is Gaurang Raje. Just wanted to ask, as you mentioned that I'm audible, by the way, right?
Yeah, you're audible.
Yeah. So you mentioned that an option would be to create a paper as a result of the project that we would be making. That would also
I hold on. I don't know if you're breaking
writing a
off just
paper
for
and
me.
then publishing that maybe.
I don't know if you broke off just for me, but you broke off in the middle there. I'm so sorry.
Am I audible now?
Yeah, you're audible.
Right. So writing a paper as a result of the project that we would be creating, how would that be possible on such a short timeline that we have? So writing a paper and then maybe publishing it, is it even possible?
That's a great question. And for the most part, it depends on the problem you choose. So in my view, it's not that hard to apply existing methods to a new data set. For example, if you, and this is something I was advising a student about, which is a political science problem where we were discussing how, again, I'm going into some nuances, but how lobbying affects the policies being created by the US Legislative Council. And all of this data is available online. So it's a matter of putting one data set together with another and examining the correlations there. Sure, that is a very, very basic approach, but that is already a very good problem and a very good analysis. And this is one student working on this for about 9 weeks. So I would imagine with 3 or 4 people handling different aspects of such problems, it's fairly reasonable to expect at least like, and again, I don't know the difference. I don't know if you know the difference between workshop and conference papers, but basically conference are these big venues where you publish. Workshops are small mini venues within conferences, which are much easier typically to get accepted into. So I definitely think a workshop paper is a reasonable expectation for you to have if you perform at the best to the best of your abilities, or at the highest level of students in this course.
Right. Yeah, that answers my question. Yeah,
Mm-hmm.
I research into that then.
Sounds good.
Thanks.
Thanks for our question. Anyone else with questions? Yeah, I see a raised hand. I don't see who, but there's only one, so you can unmute yourself.
Hello, am I audible?
You're audible, yeah.
So yeah, so when we're talking about team projects, are we going in the? I actually saw a list of projects on the same website to dive into deep learning. So are we going in that direction? Is it the difficulty that we're talking about?
Not necessarily in that the direction of projects there is very broad. However, I do see that most of them were just deep learning applications, if I'm not mistaken. Maybe those are the ones I read. I would not limit myself to that. I would think a little broader in terms of at least like a lot of you are very well aware of problems that India would be facing that are solvable problems. It's just that no one sat and solved them because it's either too niche, the data was not available before, or simply that people lack the time and effort to sit and put two and two together, like I described before, but although that was a US based problem. I also explored like data.gov and looked at the data sets that the Indian government is releasing. So ideally, you want to pick problems that are super relevant to you personally, because by definition, you are the expert on those problems. You are the expert on who is dealing with these problems, how they're dealing with them, and what sorts of solutions would be reasonable to build. I don't know if that answers the question.
Yeah, thank you.
Fair. I'm going to give it another minute and then move on because we're half an hour into the lecture. Okay. In that case, yeah, the one thing I forgot to mention earlier, we did post about we will be looking for a set of students to hopefully join Unicode research, or at least that we would want to join Unicode research. Following this, that was the opportunity that was mentioned. Unicode research is essentially the small group of people that try to discuss research problems and conduct research, much in the same way as you guys are building your research projects, except slightly longer term. Where we also have mentorship by a certain staff research scientist at MIT, and we collaborate with a few other people on and off. At least the plan is to. So myself, I actually skipped over my own introduction. I'm a PhD student at NYU Data Science. I used to work in Switzerland at a physics research lab called CERN. We used to do particle physics research and deep learning. Before that, I was an undergrad in India. I studied computer engineering at TJ Sangvi College of Engineering. I did a bunch of internships, learned a bunch of stuff, got a bunch of different experiences in computer vision, graphics, machine learning, cybersecurity. What else? I think that was about it. And a lot of software development. A lot of software development, hackathons, building stuff myself, working for companies, and it was cool. So that's sort of where I'm coming from. I'm also approaching this from an engineer's perspective. But I spent the last 2 years basically gaining more statistics knowledge, thinking more about the fundamentals. And so that is the idea. That is my background and why I'm teaching this course. Hopefully that didn't come too late in the process, but yeah, that's where we stand. And so the evaluation becomes all the more important for us. Like, sure, we want to see you interested in joining Unicode research, but also we have a very limited bandwidth. So we're not looking to expand to more than, say, maybe 15 to 20 people. But again, I won't put a number. Like I won't say that's a hard number. It again depends on how many talented folks we reach out to and how many of them actually want to continue to work on such things. So yeah, that was important because someone had asked us about that and we didn't answer that at the time. So hopefully that's clearer now. So the evaluation is one part of it, like your midterm, your projects, your proposals, your readings. The commitment is another part of it, but participation is super important. The entire reason Unicode started was because students were willing to participate, mentor others, admit that they might not know the answer, but work together to find the right answer. So for the most part, we're looking for those kinds of people. Like it's might even be okay if you don't have a lot of experience, but as long as we can see the progress that you're making in the time that you have, that's good enough for us. So yeah, that's with that, we can get started with deep learning. So for today's lecture, we're going to start super basic. We're going to start with a lot of applications of deep learning and machine learning. And we're going to start with the linear algebra and spend a lot of time understanding like what makes these algorithms tick, like where does scalability come from, why does it work, what are these GPUs that typically rely on vector multiplication, matrix multiplications. And we'll close with a bit of notation in terms of just people who haven't got extensive experience with Python. I'll give them a brief idea of how we implement these vectors and matrices in Python and like just like a 3-minute refresher on how we work with them. So to start off with, the real starting point or the first stage in the story, which is not the absolute first point, but the first major pivot in the last decade for deep learning came in when someone introduced this ImageNet challenge. Some people at Stanford built out this large data set of images with 1,000 or so classes. And they said, okay, when you say classes, you mean dog, cat, boat, aeroplane, whatever. There are these classes, and then there are images corresponding to each class. So you might have different images of airplanes from different angles and different settings, all labeled under airplane, and so on for about 1,000 different classes. And they said, okay, now the challenge is to build an algorithm that can accurately classify each of these images without seeing these classes. So again, having seen some images with the correct class labels, the goal is classify the rest of the images with the correct class labels. And turns out people were not doing very well. I should have a pointer here, unless you can see my cursor. If you can see my cursor, please say yes. Okay, cool. Thank you very much. So if you can see my cursor, then I'm pointing at the initial stages of this challenge back in 11-12, when teams did okay, but they had at least 25% of misclassification, where they could not predict at least 25% of the images correctly, could not predict the classes correctly. And then in 2012, there came in a team and they said, okay, well, we use deep learning, and the error rate was actually below 25% by a lot. And wow, that seemed to work out really well. And everyone was like, oh, what are they doing? And they created this convolutional neural network architecture that worked out for them. The following year, for obvious reasons, everyone looked at what they did, and they also developed better approaches rooted in deep learning. And the pattern held. Like every year, people use more and more complicated architectures, new advances in the tools and techniques to classify images, and they basically built out better networks to the extent that it's basically now a matter of a few decimal spaces in the leaderboard rankings. So it's super intense. Like just a few percentage points improve, a few. Yeah, you get the point. It's a intense competition, and like every decimal space matters. So that's where we're at in just 7 years or 8 years of experimentation for this challenge, which is a huge deal. Like you can think about it as, for years people thought of these algorithms like backpropagation. For those of you who don't know what backpropagation is, it's basically just saying, if I do something wrong, how can I get myself to do something right? Basically, there's a feedback that goes through your networks, and we'll get to that in a couple of lectures. But the idea being that basic concept had been discovered long back in the 90s. There was nothing new about backpropagation, but the fact that they applied that at scale and it worked in a real world problem was a huge deal. So, and this is a general trend in machine learning. Like a lot of new techniques, or I would have to, if you can see me, I'm doing air quotes, the new techniques are really like old techniques from different fields repackaged and applied to deep learning and presented as very new, which is why there's a lot of discussion in the field, like, oh, you have to cite the right sources, and my source is older than your source, which just means like someone I know wrote it before someone you wrote, someone you cited. So there's a lot of discussion about that, and it is fair. Like you should cite the right sources, but sometimes it's super hard to tell who invented what, because they're from so many different fields. We have biological inspirations for neural networks for obvious reasons. Neural networks are based on human biology. We have physics or inspirations coming from statistical physics. We have a lot of applied math inspiring new machine learning techniques. In some cases, I think there was epidemiology, but I'm not going to commit to that. Anyway, you get my point. Lots of different fields inspiring new neural networks. And so, yeah, lots of old techniques that come back, get repackaged, and get sent out in new packages. And backpropagation was known before they came about this advance, long before they came about this advance, but it was really like this pivotal moment where this gap you see between them and the competitors, which is the purple dot and the light gray dots, which made people look up and say, oh, deep learning, okay, cool. And it's just been all the way uphill from there. I would say downhill, because it's just easier to apply deep learning since then. And yeah, that's all I want to say about that. Oh my God. Cool. So let's get into some applications of what deep learning is doing. It's not just classifying things, it's also like segmenting images and detecting objects in the image, which is, if you think about it, for a computer, it's not going to see all of this. It's going to see numbers in a matrix. Why numbers in a matrix? Well, because this green is only represented as in a matrix form. Like every pixel has a value, right? If you have RGB values, you have R0, B0, G255. I think that corresponds to a green color, pure green color, or whatever you label that as. And so it's like hexadecimal values, or basically like matrices of numbers that correspond to each pixel. So for a computer, it's super hard to exactly identify the boundaries of this, and then place a box over it, and then identify what kind of object might be in the box. Which makes it even cooler that it works out so well in practice. That's all I want to say about that. So there are open source packages available to do all of these things these days. And Alex Mola offers one of them here. It's called MaskRCNN. Take a look. If 99% of the time, you will find a good tutorial also implementing these things. So it's not just that you have to look at the code and magically understand what the algorithm does. Well, you can also run it in a notebook that someone else has created, which is really how Colab makes life much easier. Colab is Google Colab. You will get into it in the recitation tomorrow if you don't already know about Jupyter notebooks. Cool. I'm confused why. Okay, cool. Okay, another cool idea that came about after this ImageNet revolution, style transfer. So if you have a certain image or a certain painting that an artist created, which has a certain style, for the uninitiated, every artist has their own style of painting, but there are also like conventional styles. I forget the typical names of these styles of art, but it corresponded to different eras in the evolution of art. So what the goal of style transfer is to say, here is any sort of image, here is a painting which has a certain style to it. I want you to take the style out of the painting and apply it to this image of mine. And one popular thing people do is take their selfies and upload it and apply different styles to it. And it's so popular that there are multiple mobile apps that do this for you. Filters. It's essentially like saying, here is a certain kind of filter I want to incorporate into this image. Except it's not just an overlay. It's like updating the internal parameters to generate this new image that is similar to the old one, but now in this new style. So that's style transfer. The crucial idea there is you don't want to change the original image. In the sense, you still, if it's boats and a certain building, you still want it to be boats and a certain building. You don't want it to be a person coming out of the style transfer. But so that's the key part. I don't know why okay, let's go with that. Synthesizing faces. So a couple of years ago, there was a scientist called Ian Goodfellow who was working at this Canadian institute. He came up with this technique called generative adversarial networks. And the goal of generative adversarial networks was to say, okay, let's consider a game where I have two players, and it's a game of cops and robbers. where the robber has to create this fake item and replace some original item with this fake item, and the cop's job is to be able to tell which item is fake. So if you think about this as like a robber stealing something from a museum, which is like n number of Hollywood and Bollywood movies, basically you replace the true item with a replica, and the replica has to be so good that a cop cannot tell the difference between this new item and the old items and the old original item. So the same thing was applied in an algorithmic setting, except now for people and their faces. So what you do is you want to be able to generate new faces that are not real people. Like these are completely generated by the algorithm, but they look so real that you might not be able to tell if it's a real person or it's a fake person. So all of this technique that Goodfellow invented was then applied in this setting to generate some super realistic faces. And there are other ways of doing that, but that's just one of the examples that seemed prominent enough to mention. So yeah, like with machine learning, you can also synthesize these faces. And that's been applied in a lot of ways. One side note that I wanted to mention was that a lot of these old courses don't actually get into the ethics of doing something. Like they tell you a lot about, yes, this is what machine learning is capable of, but you don't discuss as much what the cost of failure is, or in what bad ways, or alternatively, in what bad ways these algorithms could be applied. And I think that's a super important discussion. Like my personal opinion is that it is super hard for an individual to always make decisions purely grounded in morality. Like if you don't have enough money to feed yourself and your family, tomorrow if a company asks you to do some work, you are probably not going to question the ethics of it, because they're paying you for food. But that being said, with most people in data science not facing such dire life consequences, I think we need to have a more clearer discussion about the ethics of certain algorithms, and we'll definitely get into that, but I figured that was important enough to mention. Yeah, so at least to the extent that you can, and to the extent that you think, you should hold yourself to some accountability, regardless of whether other people do or not, when it comes to the ethics of doing things. And I also have my personal opinions about that that I won't get into right now. But back to the applications of machine learning. One of the other cool things that you can do with machine learning is generate these embeddings for certain words in certain spaces. So if you think about embeddings, and I ask because we haven't gotten into higher dimensional or latent spaces, but let's just think about it in a three-dimensional space, since we have the plots that Alex Mola has nicely created for us. So if you plot the word king in a certain space, so you convert king into some numbers, you reduce that to 3 dimensions, and you plot it here, and you plot the word queen at a certain point, you would expect a similar sort of relationship to hold between man and woman, because just by virtue of king is to queen as man is to woman. In a similar sense, you want to consider tenses. Like this typically comes in for a lot of language models where you want your word embeddings to make sense. And this is what one way of claiming that they make sense by just visualizing how these relationships occur. So walking is to walked, which is present tense, is to past tense, as swimming is to swam. So you want to maintain you want your embedding spaces to be able to maintain these sort of distances. Why do we want this? Well, because once you know these sorts of distances, then all you have to do when you have these questions, so suppose you have these countries, you have a column of countries and you have a column of capitals, right? And some of them some of them you don't know. Ignore these blue lines in the middle. So if you know that China's capital is Beijing and you want to find Japan's capital, then for your algorithm, you want to give it China and Beijing, and then ask it a question of China is to Beijing as Japan is to what? Or equivalently, you've given it a bunch of different examples. It has learned some relationship, which is capital of, and I'm just naming that relationship. So probably the wrong name for the relationship. The relationship should probably be named capital is. It's just easier to remember semantically. So China's capital is Beijing, Japan question mark, and then the algorithm applies capital is and comes up with the answer Tokyo, because it has this embedding space where it sees these different points. It has the point China, it has the point Tokyo, so it knows the direction you want to go in. It has the point Japan, it knows the direction you want to go in, and it arrives at Tokyo. So that's this intuition of why you want word embeddings to be embedded in like this meaningful space, as opposed to just arbitrary embeddings. And TensorFlow actually has a nice word2vec tutorial, but I would also say it has a nice word2vec projector, word embedding projector. I will share a link to that. I've played around with that a bit, and it seemed super interesting to see what words are embedded in like close together and T-SNE and all that, just playing around with that to school. If you don't know T-SNE, that's fine. It's just a certain technique of reducing this. Like I said, 3 dimensions is easy to visualize. If I tell you 7 dimensions, you probably won't be able to plot it on paper. So it's T-SNE, never mind. We will get into these things later. Right now, I just want to talk about applications. How are we doing on time? We are 1 hour almost into the lecture. I want to give you a break at 1 hour. And I have 5 more slides to go. I think we should be good. Machine translation. Machine translation talks about, as you might have already guessed, translating between languages. So you give it a sentence in English, and it has translated that sentence in a different language. So here we see German to English. And this is just showing how Google Translate has improved over the years. Cool. That is machine translation. There is a lot more to say about each of these subjects. Like there could be a university course organized around machine translation. So I am clearly oversimplifying a lot of these things, but that is because we don't have the time to get into a university course for one slide. There is a text synthesis problem where you want to synthesize a sentence with a certain style. I don't want to say more about this. Yeah, it just has to know what words, how to modify a sentence with a certain style. So I guess you could say it has some analogy to style transfer, in the sense you have the image, you have the style, and you want to create the updated image in this style. I don't know if this is the approach these people used in this paper, but seems to me like that might be an intuitive way to think about text synthesis. But I'm pretty sure text synthesis came before style transfer. Yeah. Question answering is another very, very cool area. So there's question answering got a lot of emphasis, at least back in 2018 and 19, I think, when some people at Georgia Tech Facebook came up with a very cool problem statement where they said, now we have this visual question answering data set. Anyway, I'm getting into too much detail. The goal of question answering is, given a certain image, you want your algorithm to be able to answer any sentence or any question asked about that image. So this is a very notable example in the sense that her mustache is made of bananas, right? So you want the approach you take to answer this question is, you want to extract the objects and entities in this picture. You want to understand what the question is about, which entity is the question about. You want to understand the relationships between these entities, and then you want to arrive at the answer. So there are a number of moving parts within all of these things. And I don't want to get into the details of attention, but for now, when I say attention, I just mean which part of this image should the algorithm focus on. There is a lot more to be said about attention, and especially in 2020 and 21 with there was a new architecture called transformers, which was based on this idea of attention, which got a lot of traction and is still continuing to get a lot of traction. So hopefully we will get to the point in the course where we discuss this. I think an entire lecture based on transformers and attention. Last three before we take a break. Image captioning, right? So given certain examples of captions and images, and given a new question image captioning is about generating a particular caption for a certain question query image. And this is super cool. And again, it involves a number of moving parts, because you want to not only identify the entities and their actions, but also like the relationships. If there is something happening, like a glass is being held in a hand, could be an image. So yeah, you should look up visual question answering. That should give you like a very cool overview of these kinds of problems and how people solve them and the progress made thereafter. Another cool example of applying AI that came out in the last decade is by this company called DeepMind, and originally also I think by IBM Deep Blue, that beat Garry Kasparov. Garry Kasparov was one of the best chess players in the world. At least he was a grandmaster in his time. He was rated number one, FIDE number one in his time for a very long time. Before Anand, and he was also the mentor of Magnus Carlsen, one of the early mentors of Magnus Carlsen, who is the current world chess champion. Anyway, the point I'm trying to get at is it was a huge deal for a computer to be able to beat a human at playing chess, which might not seem like the case for a lot of us, but back then computers were these not as smart machines that were very clunky, that were very difficult to work with, and it wasn't intuitive that, oh, the computer can easily beat people. So them showing that was IBM Deep Blue, I think, was the first. But eventually DeepMind came out with even better algorithms. DeepMind is this AI company that Google has acquired. DeepMind came out with algorithms to that play chess in an even better manner. And one of the coolest things is it actually uses a super intuitive idea that you might actually implement yourself while thinking of. So when you play chess, you think of different potential outcomes, right? So if I play my king to this next spot, will my opponent's queen come and attack the king? If my opponent's queen attacks the king, do I have a defense for it? If I have a defense for it, can they attack the defending piece? And so you build this tree of potential outcomes. And what the algorithm also does is search through this tree, except like in a very fast manner, because naturally computers can think faster than people. At least that's what I think is fair to say. However, there is this game called Go, which has an even larger set of possibilities. Like in chess, we have I guess 16 pieces. No, wait, my bad. I should know this. I used to play chess a lot. Yeah, 16 pieces per player. So there are like 16 times whatever number of moves each piece can make at each step, right? Go is not the same. Go is a bit different. Where there are way more possibilities. And what's super cool is that the algorithm is still able to go through those trees of possibilities. It's called Monte Carlo tree search. I don't know if AlphaGo, the algorithm DeepMind created, also uses it, but I know the initial chess playing algorithms definitely use this tree-based search. So a lot of these things, the point I was just getting at is a lot of these things are super intuitive, but no one explains it like that. All these papers that you will read will explain a lot of math, throw a lot of things at you, and you will really have to find the right people who will sit and talk to you about, at the core, this is what is going on. And really that's what I hope to do throughout the course. Why am I the right person to talk about that? Well, because I'm super confused by a lot of these things, and it takes me a while to sit down and think about, well, but really they're doing something quite simple. Yes, but they had to In a separate lecture that is not recorded, I will rant about the publication process and how papers used to be so nice to read and understand. And a lot of papers these days are not really up to that quality, and how I am also part of the problem because publication is an essential part of PhDs. But yeah, that is my take on why it is super hard to read a lot of research papers these days. On the other hand, you have a lot of videos and tutorials and lots of people trying to deconstruct them. So I guess it evens out. But yeah, a lot of complicated algorithms have something super simple at their core. And you want to try and find that super simple thing so that you can translate that into solving other problems. Last slide before we take at least a 10-minute break. The tools that we will use to study this are basically Python and Jupyter, and this is more to do about the recitation than anything else. If you have any issues with Python or Jupyter, please let us know. You shouldn't have issues because all of this is installed in the environment that Google offers called Colab Notebooks, which I assume all of you are familiar with. And I mean every single one of you because you have submitted your assignments in a Colab notebook. And that is all the flexibility we need. We won't be going too much into the details of what Colab is, why you want to use it. But anyway, with that, I will take a 10-minute break. I will first take a 5-minute set of questions, and then we can take a 10-minute break, and you can come back for the linear algebra section. So I will pause for questions.
I have a question.
Sounds good. Go ahead.
So, with the advent in like machine learning, the chances of like crime and like wrong practices being practiced is also getting increased. So, while thinking of a project or taking something into action, what measures should we look into so that the crime rate decreases, or at least it doesn't get increased? Basically, like what should be your aim, or what should be your thinking process, thought process?
This is an excellent question. Thank you for raising it. I mentioned this very briefly, and I should preface this with the fact that I'm not an expert on ethics. But I will say that in general, I think what your question is getting at is how do we avoid amplifying biases that typically enter the picture when data scientists design algorithms without extensive thought on the social and humanitarian implications. The first thing I will say is you want to at least like do a cursory check about is there literature that examines how the class of algorithms that I am using is biased. So for example, face generation, there was a lot of discussion of biases because it essentially keeps generating faces that are of a particular ethnicity. And when you try to apply the same to other ethnicities, it doesn't work as well. There were some biases on classification. Actually, I think I was talking about classification of faces, which performs, so the face classifiers perform much better on faces of a particular ethnicity than another, which is really not fair. So I guess I could point you to a couple of lectures on fairness and transparency because I'm not an expert. So if I had to teach you, I would also review the same lectures and teach you. But I feel like you don't have to, don't limit the kinds of project proposals you think of because you think it won't be fair. Try to think of the project proposal and then think about like, okay, now what are the implications of this and how do I improve this? Because that gives you enough ways to advance the literature as opposed to just say, no, I can't work on this because none of these things are fair. That's probably true for very few things. Again, I'm saying this in the context of the course, in the context of the projects you will take on. So in that sense, unless you're doing explicitly crime rate prediction, I would say you don't have to worry about like right at the start that this will not be fair, as opposed to like at least chalking out a basic problem, coming to us and then discussing the implications of fairness. Like don't limit your thought process. It is both our jobs to discuss fairness as opposed to you just stopping to think about some project ideas because it has social implications. I hope I got the answer. Yeah. We still have 3 minutes, so feel free to shoot your questions. If not, you can go ahead and take a break.
I have a question, but I don't know. It's not about introduction. It's a quite specific question. Is that fine?
That's fine.
See, I was seeing a lecture about there was this Sutra model that one IIT professor had made on the COVID-19 issue, which actually had predicted the curves pretty perfectly throughout the world. So what he said was a lot of like statistical measures and deep learning measures are not used in social network analysis and stuff like that. So he says that there's a lot of scope in those kind of domains, but I don't know what exactly is that. So I would like to know about that.
You picked on a pet project. So my current area of research is focused on social network analysis. And this is true what the professor said to some extent. Like there are disconnected fields that examine social networks in the sense that a lot of social networks can be thought of as graphs, and there is a lot of work in graph theory. But that's not necessarily done using like deep learning practices. So no one sat down and connected a bunch of threads is what you want to say. But there are these threads and there is opportunity to apply deep learning to social networks. Another aspect of what this statement might mean is there is a lot of multimodal data. What do I mean by multimodal? Well, there is a lot of user tweets. There are a lot of user retweets and all of that, which is text-based data. There are a lot of images that a user shares, which is image-based data. There are videos and GIFs that people share, which is video-based data. There might also be audio if you want to combine some different platforms like Facebook sharing some, or videos having some audio or whatever. Point being, like these are called different modalities of data, and multimodal analysis of social networks at a large scale has not been explored as much as say image-based analysis has been. So there are a lot of applications like you can directly transfer from images and videos to multimodal social network analysis. There are discussions of politics and causality and like what makes people think and behave in the way they do. So explaining engagement, maybe like what makes you like that tweet and not this tweet. And can I predict which tweets you're going to like more? There is already work on that, to be fair. But there is, again, a lot of scope to apply new and existing work from other areas directly into social network analysis. Obviously, with respect to the course, you have to chalk out a bite-sized problem because you're not going to be able to train for like 2 weeks and then see one result and then say, oh, I did something wrong, and then train for another 2 weeks and then see one result and that sort of thing. Even assuming you have the resources to do that. So like I said, you want to carve out bite-sized problems that you can at least present a basic research project on. This doesn't have to be like publication quality work, but it has to be interesting enough that you would like, just as an evaluation, you would be interested in continuing. So as long as we achieve that, we are happy with what the course gets to you. I hope part of that answered your question and gave someone else more information.
Swapnil, someone has raised the hand. Someone has raised hand. So
they would have like that's okay. I see. I wasn't looking at participants. I was looking at chat. Yeah, please go ahead.
Yeah, hi. Am I audible?
Yeah, you're audible, Aditya.
Yeah, so like my question was like in the terms of the project, I don't know if it's too early to ask about it, but then like one question I always have in like the college projects as well is that how do you map a sort of working project or an app or something that's not restricted to, you know, a data set or something like that, something that works, you know, like, and how do you map it to something like a research paper or something that can be published? Because like that is where I was looking from. Basically, I wanted to add certain accessibility features to some working apps that are there. That was like my initial project idea from the beginning, and I was hoping to achieve it in this course, sort of. So like, how do I map that to a research paper, or do I change my idea completely? Like, how would you advise?
So there are a bunch of different grades of research paper that we're talking about here. The lowest grade of research paper is a conference that no one has heard of, that is willing to take any sort of papers, that has practically no peer review process. And these conferences exist. And I know that because I have been to these conferences really early on undergrad. I was like, oh, cool conference. But like, I didn't realize then that this conference was really not good. So in terms of those levels of conferences, you can probably sit and write a paper tomorrow and submit it, and they'll probably accept it. But you don't want to do that, mainly because anyone who is going to evaluate your applications or your profile at any point is going to know. Now getting to the point about mapping a project to like a meaningful research paper, now that we're at that question, there is a certain structure to different kinds of research papers. For example, like an algorithms paper will have some sorts of analysis of the algorithm, the computation, what is different about it, comparisons with other algorithms, then showing what is the conclusion, and then discussing potential applications. So start with motivation, literature, review, discussions, experiments, and then results, which is like a general sort of approach to novel work. There is a certain sort of social science approach to papers. There are certain kinds of survey papers where you just conduct surveys of different literatures. There are comparative analysis where you compare different kinds of case studies and specific things that match about them, specific things that don't. For example, the impact of universal basic income in India versus the US in a hypothetical world, right? So those would be like the comparative sort of analysis. So you want to figure out which class of papers your project fits into, and then figure out what is the conventional structure of papers in that area, and then just adopt that structure and then fill in the details of what your paper does is different. And I described this in a mechanistic way for a reason. This is not the only way to go about it. But if I was a student and I want to maximize my chances of getting accepted, getting my paper accepted at a certain place, then I would just stick to what this does. And I say this coming from a place where I am currently debating with people about rebuttals to my papers, which argue that the paper structure is not great. So they buy the science, they just don't like the structure. So yes, there again, like I said, there is a whole discussion about the peer review process and my opinions. But it seems to me like this is the low-cost approach to structuring your projects and framing that work as research. If that didn't answer your question, I'm willing to go on and talk for longer.
Right. Just a small additional question. You mentioned the concept of being novel. Like, how does that pan out? Like, if is it considered novel if I take two existing things, smush them together, and give you something, or like, does it have to be completely from the ground up novel? Like, how does the concept of novelty work in research technically?
Concept of novelty works based on the evaluations you present. It seems to, again, I don't have a general answer to this. It varies a lot based on cases and people. And I also would argue that I'm still like a mid-career PhD student, and this you want an authoritative figure to answer this, but to the extent that I can, I will try to answer this. For me, novelty, the arguments of novelty we presented were from different application perspectives, saying that, look, these problems considered, for example, hashtags as just equal, like all hashtags are okay. We looked at hashtags as these are trending hashtags, these are non-trending hashtags. Like these might be popular, but they are not trending. So if you look at content virality, a lot of it has to do with trends. So if you tend to use trending hashtags, you will see your content trending in a much easier manner, right? So that was my argument for novelty, considering like hashtag recommendation and trending hashtag recommendation. I don't know. I maybe I'm biased because it's my work, but it seemed to me that would have been enough for novelty. But conventional cases of like how people approach novelty is to show failures of existing algorithms and how we solve those problems. And to some extent, we also did that. I didn't speak about that. But anyway, that seems to be clearly accepted as novel because existing popular algorithms fail here and we solve this case, or we do better than their failures.
Understood. Thanks a lot.
Sure. Okay, if that's all, then we will take a 10-minute break and I will be back to discuss some linear algebra.
Hello, Swapnil.
Oh, yeah.
Can you hear me?
I can hear you. Yeah, go ahead.
Yes. I had this question about the phase generation technique that we were talking about. Can you explain in a basic theoretical manner what would be the algorithm of it, or what might it be doing inside while figuring out a phase?
The cops and robbers, or just generally phase generation?
I'm sorry. Can you just?
Are you specifically talking about the cops and robbers setup I described, or just generally phase generation?
Yes. It can be general also. I just want to see the algorithm. What kind of algorithm they might be using?
Right. So I'll start with generally what phase generation is about. Typically, what people these sorts of models belong to a class of deep generative models, which for obvious reasons are called generative in nature, because they start from some noise and eventually end up with a phase. So they generate these phases. I don't, I mean, I'm not an expert on other kinds of algorithms on phase generation. So I'll start with cops and robbers, which is basically called generative adversarial networks. What they're trying to do, so there are two goals, like you train two networks. One network is the generative model or the generator, and the other is the discriminator, which again, discriminate is like figure out which one is the true image, which one is a generated image. So what you do is you start by, again, I'm trying to keep this discussion still very high level so that you can think about other applications where GANs might come in. The goal of the generator is to keep throwing more images that look similar to the original data set, where you have this data set of real people's faces. So you want the generator to create images that look similar to this data set. And you want to be able to fool the discriminator into not being able to classify the true versus generated faces, or simulated, or whatever you want to call it. I think that explanation should suffice for now.
Yes, it did. It did.
Yeah.
The part about the discriminator. So if I don't have enough database for that, I would be creating a very low-level phase generator, I think. So for phase generator to be working at its optimum capacity, I need like a very huge amount of data of billions of people to make it look really authentic.
It seems not to be the case, because you can do it in a far more efficient manner than needing billions of examples, because at the end of the day, a face is composed of a fixed number of parts, right? There is one nose, there are two eyes, there are two eyebrows, there is one mouth, there is one head or hair or whatever you call it, two ears, and probably some nuances about the colors of all of these parts, right? But that is a finite set of pieces. As long as your algorithm can learn to put these pieces together, it seems to be the case that it can generate reasonable faces. No, I can't hear you if you're saying something.
Yeah, no, I said it answers my question. Thank you.
Oh, okay, cool.
Hello, Swapnil.
Hey, Shiv.
Can you hear me? Yeah, I wanted to add to that question. He asked, how does if I want to generate a new face, how do we give the model the necessary signals so that it tweaks something to the extent we want? like changing the shape of the nose or just tweaking it certain differently? Like how are we ordering this like generator to generate something what we want?
This is a great question, and to some extent it has to do with interpretability of this backpropagation algorithm, at least to my understanding. What you want to do is make it super expensive for the generator to do something wrong. So for instance, if you put a face on top of your eyes, again, this is, I don't know the correct answer to this. This would be my answer to this, that your loss function is structured in such a way, and the TAs can feel free to jump in if you have better answers, because you probably also have different experiences from what I have. So to my understanding, you want to constrain it in such a way that putting your nose on top of your eyes is a much wronger thing to do, or is much more expensive for the algorithm to do than putting your nose like very close to your mouth, because this is still reasonable, this is unreasonable. Hopefully it's a hand wavy explanation, but you can express that algorithmically is my point. Does that?
Yeah, okay. So like it all depends upon the like application that I'm building to which like I'm giving the commands to generate, right? So it depends upon the software that it is, and not how the discriminator works or like the generator works. Was I clear?
I think so. So you're updating the way the generator works though by creating this loss.
Okay.
So you're forcing it to go in a certain direction.
Changing the loss function.
Yeah.
Okay. Yes.
And your loss function is the reason I'm saying this is your loss function is essentially combined of the difference between this simulated image and the original image. And the original image on average, like if you take all of your images and average them, you're going to have on average the nose in the center, the eyes on the sides, the mouth below the nose, and like the face around it. So
yeah, but like we are changing the structure, right, of like when generating some image. So how are we like tweaking the small bits so that we like, for say, if you were to swap your face with something so that you look like a woman, say, per se, like just an example. So yeah, so there might be some tweaks that your facial structures might need. So how do we command the the model to generate that kind of feature?
I think I know what you're asking me. I might have an image for this. Like I know where the answer is. I don't know what the answer is. Let's look at glow. Again. Nice. Glowgan is now glue gun. I think this kind of thing is what you're asking me about, like the same person, but like with modified features.
Yes.
Like how do you go about this? So you probably want to go and either watch a tutorial about glow or like there is this idea of style GANs.
That's the correct way, yeah.
Yeah.
Okay.
Yeah, I don't have the answer, but I know the answer is here. Cool. Okay, we are still on break. Okay, so the question Sahil posed was, if I am not good at one of either linear algebra or, could you repeat please?
Probability.
Probability theory, then yes, hypothetically is important. If I'm hypothetically not good at either of probability theory or linear algebra, can I just not do deep learning? I think it is fair to say this is flat out untrue, because most people, at least in the engineering perspective in deep learning in the field, have a very cursory understanding of all of these things. Like they are not statisticians, they are computer engineers like you and me, trying to, or at least like me, trying to attempt to understand all of these things in probability theory and deep learning. And at least for my part, the only reason I understood these things was because I got great teachers at some point. It was not like self-studying that got me through. It was this emphasis on, like, some people taught me really well and at least equipped me with the basics to understand things myself thereon. And that is hopefully what I want to do for you. At least I want to teach you the basics enough that you're confident in moving forward. The only difference between, at this point, I would say, a hypothetical person who's not good at one of these things and me is I have the confidence to say, I don't know this, but I know where to find the answer to this. That is the only difference. And that confidence is key to knowing more about deep learning and not knowing. I think that's the only thing. It's not about knowledge. It's about the confidence of admitting you don't know it and finding the answer. That to me is the difference. So firstly, flat out no, you can work in deep learning in an applied sense without knowing exactly what is going on in terms of the mathematical knobs. And people do this. That is why I can say with confidence that this is the case. I don't know if it's right or not. That's a whole different argument. And I don't know what problems emerge. That is also a whole different argument. But you can do it. That is, yeah.
Makes sense. Thank you.
Mm-hmm. Cool. So with that, we'll get quickly into how important is it to understand. So Mohammad Sharik Nawaz asks, how important is it to understand the math behind an algorithm intuitively on a ground level? Also, how do we translate the basic intuition while reading or implementing techniques? Two good questions. I will say save this towards the end of the lecture because I want to get into linear algebra right now. And we have barely 25 minutes and I want to do it justice. But ask me this again if I forget to answer it after the end of the lecture. I'll be on for a while after. Okay. Let's go to Keynote, linear algebra. I will breeze quickly through scalars and vectors because we at least assumed an understanding of matrix multiplication when we gave you the assignment. And for the most part, at least most of you got the numbers correct and the dimensionality correct. So I will assume you at least know what these simple operations in terms of scalars are. Yeah. A plus B is an addition operation. A dot B is a multiplication operation. C is equal to sine A is just a function applied to A. So the function is called the sinusoid function. And A is the parameter or argument to that function. A plus B. Thank you very much. Wait, I thought I was already recording, but okay. So I was just talking about scalar operations. Length of A, mod of A plus B is less than or equal to the length of A plus B is less than or equal to the length of A plus the length of B. I assume this is understandable by everyone, so I'm not going to spend a lot of time on this. Length of A dot B is equal to the length of A times the length of B. This is fair enough. Let's move on to the next one. Simple operations on vectors. Here now we use the same thing. C is equal to A plus B, but here what we mean is CI, C sub I. So this, my cursor, hopefully still visible, is this is, I can annotate. Cool. This subscript I is just indicating an element of. So C is a vector which has some elements. 1, 2, 3. Again, I'm assuming you're familiar with this. Element 1, element 2, element 3. This is a bad approach. Really don't like this. Never mind. So that's an element of, and Ci equal to Ai plus Bi. Again, seems familiar for you. C is equal to alpha times Bi, where alpha is a scalar. This indicates Ci is equal to alpha times each element of Bi. Again, I'm assuming it's familiar. If it is not, then stop me. C is equal to sine of A. indicating each element ci of vector C is equal to the sign function applied to each element I of vector A. A lot of times people use shorthand notation like this, so it's important to be familiar with it. Cool. So I will use this terminology later, so it's better to explain this. This C is equal to A plus B. I'm saying C is a linear combination of A and B. What is linearity? I'll get into that in a bit. So I guess I should hold off on that then. Okay. So back to, and again, I'm assuming my screen is visible. If there's anything wrong with the whatever, just let me know. We are now talking about the length of a vector, which we call the vector norm typically. The norm of a vector, in this case, the 2 norm of a vector, we'll get into norms in more detail, but 2 norm is equal to the summation of each of its elements squared. I is equal to 1 to m indicates that the vector A is of length m. So we square each of its elements and then take the square root of this sum. And why did I say 2 norm? Well, this 2 is important because you can have any number, any integer norm. So L1 norm basically means sum of A1 raised to 1. And L infinity norm, what's that? Maybe I'm going into too much detail here. Yeah, we'll get back to that later. But what do you want to say about length or norm of a vector? Norm of a vector is greater than or equal to 0 always for all vectors A. Length of the norm of a sum of vectors is less than or equal to the sum of their norms. Again, because I'm not going to say because, I'm assuming this is all familiar, not spending too much time on this. Yeah, cool. What I really want to spend time on is this is a visual representation of the same things that we just discussed. You can watch Smola's video to just, he mentions a statement. I don't know why this is super relevant, but I guess that's because he has a programming lecture alongside, and he wants to indicate that this operation is parallelizable, like vector multiplications can be parallelized. So if this is C is equal to alpha times A plus beta times B, you can calculate alpha times A on one GPU or one core or one thread. You can calculate beta times B on another GPU or another core or another thread, and combine the two later. So it's like very easily parallelizable. I think it's called embarrassingly parallel, just because it's that simple. I don't know if that's what he means by parallel for all do, but that's what I understand the case of vectors to be in these, like in this specific case. You can do that. And we're taking a very simple case, like imagine doing that over multiple summations infinite times, millions of times. Well, that's super quick. That's why GPUs really took off when they were introduced for machine learning. Well, when machine learning started using them. Originally, I think it was gaming and graphics and stuff that really used GPUs. It's called graphics processing unit. So makes sense. Cool. So getting to dot product of vectors. Dot product of two vectors A and B is the sum of the element-wise products. Element-wise products is basically AI times BI summed over all I. This is okay. You know all of this. Orthogonality of vectors. Orthogonality indicates A transpose B. If vector A is orthogonal to vector B, it indicates that A transpose B or their element-wise dot product will be 0. There's a difference between dot and cross product. Right now I talk about dot products, so remember that. And if we have two vectors that are orthogonal with a third vector, then a linear combination of these two vectors is also orthogonal to the first two vectors. I assume you are familiar with this, but I'll give you a 2-minute explanation on this. If you have two vectors lying in the x and y axis, think about the z axis. Oh, maybe I should draw this. Let's try this. Let's see if this works. Okay, this worked. You want to go into something super simple. If I have two vectors in the x and y axis, say A and B, does anyone have or does everyone believe me if I tell you that any linear combination of these two vectors, no matter how you scale, rotate, or transform them, it will lie in this plane that is the xy axis? Like it will lie flat on my screen. If so, I'm sharing my iPad screen. So any combination of these two vectors A and B, which is going along the y-axis and the x-axis, will lie in this plane defined by the x and y-axis. Assuming this is clear, now I will define a z-axis that is coming out of my iPad screen, which is like this. And I wanted, if I was a better mathematical animator, then I would create a cool video that shows you this 3D z-axis. And this, by virtue of saying that A and B are like orthogonal to any vector in this along this z-axis, I'm basically saying that any combination of A and B will be orthogonal to any vector that lies along the z-axis. So very hand wavy. Oh, I see 8 new messages. Cool. Okay. I'm going to assume this is clear now. If this is not, please watch one of either Khan Academy's linear algebra videos or 3 Blue 1 Brown's linear algebra videos, because they have visualizations. Preferably 3 Blue 1 Brown, just because he has nicer visualizations, and he almost certainly has visualizations for every video. So yeah, I'm going to stop that screen sharing and start this one again. So yeah, that's what I mean by a linear combination. I wanted to explain linearity for a bit before moving on to something else. Yeah, let's go back. So what is this idea of linearity? Because lots of times people say, oh, this is a linear combination of other two vectors, and this is a linear.
Swapnil, your screen is, are you sharing the iPad screen?
Yeah, I'm going back to the iPad screen slowly while I'm talking. Sorry. Yeah.
Okay.
Oh, it's visible. Yeah. Is it visible now? No, it is not.
Not yet.
No, it is not. Sorry. Okay, cool. We're back. So by linearity, there is a two-line definition of linearity, which is so intuitive that you will be able to, if you remember this, you will be able to replicate it at whatever point. Well, there's a one-line definition actually. F of alpha A plus B is equal to alpha times F of A plus B for linear function F. So I'm saying if this function F is a linear function and I apply it to any two arguments A and B, where I multiply A by a scalar value alpha, then the way I can also do this, like this reduces to alpha times F of A plus, oh, oops, I missed out on F of B. If you remember this line, this is how you define any linear function. And that's it. Like, it's as simple as that. If you want to make it even more clearer what I'm talking about, maybe you want to replace this with X and Y to indicate variables, and you replace this with C, just like conventional notation where you use C for constants, use X and Y for variables. Hopefully this is clearer. Like, this is any linear function f. This is how you define it. So that's what I mean by a linear combination of these vectors, f applied to a combination of a and b. What was I saying? Oh, oops, yeah. Multiplied by this vector, well, I shouldn't say z. I say u, which is lying along z-axis. This is equal to u times f of. This is still going to be equal to 0 now. That was a different point that I was driving home earlier. I should not go back to that right now. Right now, I was just going for linearity. I'm going to stick with linearity. Okay, hopefully I have made linearity and linear combinations clear. This is how you define it. This is how you will always define it. This is all you need. Back to vectors. How much time? Oh my God, we are at 11 minutes. This is going to be fun. Okay. Matrices and functional analysis. I'm not going to show you the exact same thing for matrices, but the slides have enough for you to sit and understand what exactly I'm saying. I'm assuming you are all familiar with matrix multiplications, but I am going to spend time. So the 11 minutes I have, I'm going to spend on understanding what a matrix is. A matrix is a linear transform. And now that we've defined linearity, we can actually go back to the iPad, which I'm not at yet. So don't worry about that. I'm sharing. So we looked at scalars. We looked at some operations on scalars. We looked at vectors. We looked at some operations on vectors. And now we're looking at matrices, and we are saying, okay, back to matrices, and we are saying, okay, now what is a linear transform using a matrix? So the claim is that a matrix is defining a linear transform. I spoke of vectors, and in general, I'm taking like a very simple vector, which is this thing, I cap, j cap, expressing it as a column vector. And I'm saying I am applying this very simple matrix to this vector to obtain some output. Does anyone, if you have a concern with this vector multiplication being wrong, please raise your hand or interrupt me. If not, I'm going to assume you buy this. Like 1001 times I cap j cap is I cap j cap. I am going to tell you that this 1001 is equal to a certain transform, which you write as, well, you don't write as t dot, but you can write as t dot. This dot just indicates there is some argument that goes here. If I define this as my vector a, then this whole thing is equal to t of a. I'm being very pedantic about notation for a reason. When you read these machine learning papers, they're going to be like so notationally intense that you will have to sit and read 3 paragraphs of definitions before even getting to the theorem, for good reason. Like, you need to understand all of these things. But once you read 3 papers and you spend time on this, the 4th paper, the notation will come to you. Like, you won't have to think about what this is doing, what is this transform, what is this mapping, whatever. Read this Rn space and Rm space and m dimensional, n dimensional spaces, whatever. Anyway, I claim that this matrix is a transform T applied to a vector A, which gives me the same vector as the output, which is cool. So then I can then claim that this is the identity transform, because the identity mapping or transform, whatever, maps a vector onto itself. Cool. Okay, what happens when I take this new T1 mapping or transform and apply it to I cap, j cap? Does anyone want to guess? You can shout out the answer or post it in chat. 2 times scales it. Yes, exactly. 2 I cap, 2 j cap. What happens in the case below it? Now I'm here. Yes, increase, but what increases? Can you tell me the two-dimensional output? Yeah, I gets multiplied 3 times, j remains the same, exactly that. So essentially what we're doing here and what I'm trying to get at is I'm creating these, I started with this very simple case and I'm going more and more towards like a general matrix. Like all matrices are not going to be identity transforms. All matrices are not going to be simple scaling. There are going to be matrices that are look something like this. Sorry. There are going to be matrices that look like this and also vectors that look like this. It's not just I cap, j cap all the time. So if you think about it, like in the most general case, you can have this vector, you can have this matrix, and it is still, the concept still remains the same. The matrix is mapping the vector onto some space. What space? That is exactly the question that we are going to examine in greater detail in this next idea of eigendecomposition. And I'm jumping a couple of slides here in the interest of time, because I don't want to go back and share screen and go back, change screen, share. But so far, we have seen that matrices define linear transforms, which is like translate, rotate, scale, right? And essentially, a matrix can be decomposed into a sum of 3 things. Well, into a sum of 2 things, right? Into 2 parts. One is the basis and 2 is the scale. Not, this is again a very hand wavy explanation rather than a mathematically rigorous one, but we will make this more rigorous. Why am I saying basis and scale? Well, when you define a vector, let's go back to this first thing, right? When you define this vector, you say that it has an x-axis component. You say it has a y-axis component. And this is a 2D vector, 2 rows, 1 column, whatever, 2 cross 1 vector. However, you can have an n cross 1 vector, right? N can be any sorts of dimension, and that is like the dimensionality of the space it is defined on. So this essentially in the general case, this can be more, but in each case, you have a certain basis vector that you call this the basis vector, right? And so in case of some matrix, like it defines a certain, it is defined by a certain basis and it is defined by a certain scale. The same way as a vector is defined by a certain basis, and in this case, it could be defined by a certain scale. Or am I doing this wrong? I think I'm doing this wrong. I think 3, 1. Nope. Okay, anyway, I'm under time pressure, so I won't go into those many details, but hopefully you understand the point about basis and scale. And now I'm getting at the same thing, except for a matrix. And that gets a slightly more complicated representation out, but the concept is the same, where this is my scale that I'm defining my, if I have 3x plus 2y, or let's just go with the simplest one, 3i plus 2j, and 3 and 2 is my scale and I and j is my basis. In the case of the matrix, this will be my scale. I should use a different color. This will be my scale, and this will be what I call my eigenbasis. Why eigen? I don't remember the mathematical origins of why eigen, but that's what we call it. So that's what I'm going to go with. And also that's why eigendecomposition, eigenvalues, eigenvectors, and basis. So in this case, this I cap and j cap are now like these independent matrices by themselves. So this I cap, because now we're generalizing, right? So this is now in n dimensions. And along those dimensions, you have these different weird kinds of vectors and different kinds of directions which are orthogonal to each other. Yes, exactly. Thank you, Jay. He posted in the chat about how you want to decompose that vector, which I was under too much pressure to discuss in detail. Um, Again, I'm trying to give you a hand wavy sense of this because this is an entire lecture in itself, which you will find on Khan Academy and all of this. But um, yeah, we're probably going to extend the lecture by 5 or 10 minutes. And I'm sorry that I'm rushing through all of this really quickly, but at least like my goal is to give you this hand wavy sense and then formalize things. So we deconstructed this matrix into two components. The U, which is this eigenbasis, and lambda, which is the eigenvalues, which is the same as the scale and the basis. And the details of this U, you can think of it similar to I cap and J cap. So you remember what I cap dot J cap was? Anyone? Correct. So I cap dot J cap was 0. And do you remember what I cap dot I cap was? 1. Okay, cool. So you guys remember more geometry than I do. So we are generalizing this notion to now saying if this U is composed of these individual vectors, and now I'm just representing this matrix in the form of this is U1. Oops. There is a second vector called U2. There is a third column. So these are column vectors. Sorry, I should have been more precise. And so on up till UN. N column vectors. This is an n cross n dimensional matrix. We'll analyze that later. But for now, if we break this U down, then this becomes equivalent in a sense to my I cap, J cap, K cap, dot, dot, dot. So like it becomes these eigenvectors define these directions instead of your XY axis, because this is an arbitrary matrix. Like now we are no longer in this specific nice carved out case of 2 dimensions and like I cap here, J cap there, maybe Z axis, K cap here. Now we are in a very general sense deconstructing this matrix into its directions and the scale along each direction. That is the basis. That is the new basis that we are defining. If this is at least reasonably clear, where we went from a simple 2D case of matrix multiplied with vector to a general case of any matrix that we now want to deconstruct before we multiply with any vector, then it should now start to make sense that if I multiply, sorry, I should clear out this because I need some space. Okay. So let's go back and write down if my U is equal to this U1 dot 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 UN. Can someone tell me what U1, sorry, dot U2 will be? I see some answers saying 0, which is the correct answer. Can you tell me what U1 dot U1 will be? So really like this eigendecomposition thing, this complicated thing that people spend hours explaining, it might just be like easier to think of as this very simple case of you're deconstructing a matrix into its basis vectors and the scales along each basis vector, because now this is a very general case. Along X and Y axis, we took the unit scale. Along these directions, I will explain what I mean by like, we are still in a sense at the unit scale, right? Because norm of U1 is still equal to 1, where remember the norm of I cap was still equal to 1. But why do we have this scale factor? Well, now let's go back to this. So you understand now that U transpose, which is equal to, in a sense, you're taking the row and column sum. So U transpose is equal to I because of this thing. Is this clear to everyone? U transpose is equal to I. I mean, I'm doing a bad job because I'm seeing some yeses and I'm saying this is clear to everyone. So if it is not clear, please like post back to me and like write, and I will spend more time on it. But hopefully, like I've clarified that we can decompose these matrices into this basis and this scale. And now we get to like why in the world would you want to spend the time to do this? And we will take a super simple case that is very common in deep learning, because that is what the course is about and that is what we want to spend time on. Can someone tell me suppose I give you this, okay? I say that I have a matrix A. Well, no, this should have been more of an exercise, but I will walk you through it. The one of the clear use cases, okay, mod u1 is equal to 1. Yeah. Cool. What was I going for? Sorry, I lost my track. Yeah, I was going to say one of the easiest things to do is if you have this matrix A, and now in deep learning, you're doing a lot of matrix multiplications, which also might involve A square, A cube, A raised to 4, A raised to n. And this is really complicated because right now we're talking about a 2 by 2 matrix here. This is a 2 by 2 matrix. This might be an n by n matrix, and you want to compute the square and cube of n by n matrices, which is humongous in terms of computation. However, I submit to you that doing this is as simple as taking this u aside. Well, maybe I can actually prove this to you. A square, A dot A, which is really how I should be writing it, is equal to, and remember that I can write down A equal to U lambda U transpose. One thing I should mention, yeah, never mind. Yeah, it is definitely important to mention this just in case it wasn't clear. If we say U transpose is equal to 1, is equal to I, sorry, this implies that U transpose is equal to U inverse. Hopefully, like just taking the U on the other side, essentially, except for matrices. So having said this, can someone tell me what A dot A might be written as? It's hard to do on chat, but if a brave soul wants to unmute themselves and say this. Wow, nice. Okay. So Joseph basically posted the solution, which is U lambda square. I'll write it down. I'll write down why we get there. Essentially what we're doing is, and this is the correct answer, I'm just writing it down for everyone to be on board with. This is what we're saying A is. This is what we're saying A is. But considering this, we just said U transpose or U transpose U is equal to I. So this goes away. This gets turned into I. Let me erase the brackets if that makes it better. This goes away into I, and anything with multiplied by I, the identity matrix is itself, which gives us U lambda U transpose, which is lambda raised to 2. And I haven't spoken to you about this lambda yet, but why do I care about this lambda raised to 2? Well, because it is just a scaling factor. It results in a diagonal matrix because you're scaling each independent axis. right? When I say axis, I mean eigenvector, this u1. Well, so so this lambda would be a diagonal matrix. In this case, you have a nice example here, which is 4, 0, 0, -1. And scaling a diagonal matrix is super easy, because if you multiply this by itself, you will just get 4 square, 0, 0, -1 square. And that is very nice to do, because that just involves an n value multiplication. An n by n matrix has n values along the diagonal, which is just squaring n values. So you reduce this massive computation of multiplying this n by n matrix by itself, whatever number of times, into this simple squared along the diagonals, and then multiplied by 2 other matrices, which is the eigen basis of it. This is one of the very neat use cases of decomposing these matrices. There are many other applications that I don't have time to cover right now, but I will pause here and let you ask me questions about this, because this is super important.
Hey, I have a quick question.
Go ahead.
So the concept of this class is for deep learning. So how often is it the case that we take like two matrices and just kind of take it to an exponential power?
Take it to, I'm sorry, the last part, I wasn't clear to me.
So how often is it that we just take a matrices and then raise it to the power n exactly for deep learning?
Pretty often, in the sense that if you consider multiplying, if you consider the same layers with values of weights and doing the same thing for different encoder modules, in a lot of cases, especially modern federated learning, you start with the same weight vectors, you multiply them by certain values, like the images come in again and again, you multiply the same values over the epochs. So there is a lot of duplicated computation in that sense.
Great, thank you.
Yeah. This is a great question. What is the time complexity for decomposition? Because after that it is O of n, right? I will leave this to you to determine. I feel like I might have set out the answer, but maybe not. But this is a good question, and like you should work this out, because it also relates to like the practical purposes for which this decomposition is useful. I also feel like there's a better answer to that, Joseph, but I will relegate that to probably CampusFire or no, CampusFire. I'll keep my answers to CampusFire, not Discord, because I wasn't. Yeah, I don't feel like my answer was clear enough, and like I feel like I can chalk out more concrete use cases about here in a neural network is where this computation is repeated n times over these number of epochs.
I was perfectly happy with that answer, but thank you for taking the extra step.
For sure. Okay. I am going to go 15 minutes. So I'm 10 minutes over time. I'm going to take 5 more minutes just to walk you through the rest of the slides. Although they're not like super, although they're super intuitive and you have Smola's lecture, they're not like, we spoke about norms. So matrix products are hopefully clear. We spoke about norms and like the LP norm or H infinity norm. It's just, you raise, yeah. Too much. This is, we've already been over this. I'm not going to spend more time. Like I can spend it better. We spoke about eigenvectors and eigenvalues, and this is the real purpose of like what this is one of the applications of how you define not applications. This is one of the ways in which you define eigenvectors. If X is an eigenvector, so I don't like the switching between screen, but if X is like we discussed ui as the eigenvectors, now think of ui's as the eigenvectors of this matrix A, right? So A times ui is just going to result in a product of scaling ui by lambda. And I know this is super hard to just speak out, but I feel like I've discussed this enough that if you review the videos before this, you will see why this is the case if X is an eigenvector. So I did the converse. I deconstructed it and proved that this is the case. But typically, this is what you use to go back and say, this is why we need to eigen-decompose things. And I missed, I deliberately omitted this mention of which matrices can be eigen-decomposed. Typically, real symmetric matrices are what you want to go for eigen-decomposing. It's harder to do that for other matrices, but there is something called singular value decomposition that you can do for matrices that are not symmetric, like M cross N matrices. You can still decompose them, but in a slightly different manner. And yeah, I wanted to go for this motivation by changing of basis and figuring it out, but we did eigen-decomposition without necessarily relying on Cartesian and polar coordinates. So fair enough. And then I also made a list of some interesting questions you might want to think of. This is not strictly necessary for the course, but if you ever want to understand more about the theory of linear algebra, this is as much as you will need to know to go even one step deeper. Like, these are good questions to know the answer to, but they're not necessary for the course. So I just left them here. Again, these are certain kinds of matrices that I'm fairly sure you can read on your own and understand. Symmetric, anti-symmetric, what happens when the matrices are complex. Positive definiteness is important to know of, but again, this is not a linear algebra course, so we will not be using this concept as much. We already discussed orthogonality in a very detailed sense, so not going to go into that. Permutation matrices are just matrices that if you multiply by another thing, it will end up in a, if you multiply by another matrix, it will end up in a permuted version of that matrix. So either the columns will be permuted or the rows will be permuted, but they will be the same rows, just in a different place. So that is exactly what a permutation matrix is. And that brings us to the end of that section. I won't go into ND arrays, maybe a minute. In terms of code, the way you access n-dimensional arrays, you've already worked with scalars. For the assignment, you worked with two-dimensional vectors, which is matrices in the assignment also. This can generalize to like n number of dimensions, and Smola also offers a very nice example of like where these n-dimensional matrices come in and what are these dimensions corresponding to in the real world. So for example, for videos, there is a batch, for a batch of videos, there is a batch dimension, there is a time dimension, there is a width dimension, there is a height dimension, there is a channel dimension. So that's where you want to, that's why all of these computations and decompositions matter a lot. Yeah, this is not relevant. How you access this, you already know. So with that, and at 16 minutes over time, which is not bad, we arrive at the end of the lecture, and I will pause here for questions and look at the chat. Yes, I will share all of these slides right after the lecture. Fennel offers a very nice, neat explanation. All matrices are transformations, and all these transformations are linear. Like, matrices can only express linear transformations, hence the name linear algebra. Interesting. I thought about that. Okay, I will stop, and this is where you can ask me questions. I will keep recording on.
Hey, I have one more question for you. It's for recitation tomorrow. So I believe on the schedule it said, like, say, automatic differentiation is on the recitation for tomorrow. Should we do the reading in the book before we get to recitation?
I will let Fennel answer that question. I think Fennel and Aryan.
So automatic differentiation is one of the topics that'll be in the recitation tomorrow. Should we? There is a section in this on this topic on the book. Should we read that just to prepare for tomorrow's recitation?
No, I heard your question. I just, sorry, maybe I wasn't clear. I said I will let Fennel answer that question.
Oh, I'm sorry. Okay.
Yeah, so regarding, I think just knowledge of basic differentiation is fine. So apart from that, like if you know how to differentiate functions, only that's required. Other than that, no prior knowledge for that would be required. And like we are assuming everyone knows the differentiation because that was one of the questions in the assignment as well.
Oh, readings are not due before recitation. Sorry if that was your question.
Okay. I believe that does answer my question. Thank you.
Cool. So yeah, this question I had mentioned you should ask me again. It is depending on your use case, you want to spend an appropriate amount of time understanding the math behind an algorithm. So the question is, how important is it to understand the math behind an algorithm intuitively on a ground level? Also, how do we translate the basic intuition while reading or implementing techniques? I think the second part of the question, how does the intuition come in? It comes in with practice. It's just a matter of the first 5 papers will be hell to read and implement. The next 5 will be moderate, and every paper after that will be, you'll enjoy starting to implement. If you actually like the topic, you will enjoy starting to implement it and it will come to you. Like I said, for me, it's a function of confidence, because a lot of times the paper is saying exactly what you're understanding. It's just that you are like, I can't be understanding it so easily, or at least I was like that. And now I'm on the other side of it. I'm like, if I'm understanding it is probably true, I will assume that until I'm wrong. I don't know if that is the right approach, but at least that caution has tipped to a point where I can at least talk to people about this and they're like, yeah, that makes sense. And then I'm like, okay, I did understand correctly. I hope that answered the question, and I am okay with more people unmuting and asking questions. For the record, eigendecomposition isn't going to, like we're not going to, I guess it comes up under behind the scenes that you don't realize. I can find nice examples of code that uses eigendecompositions and tell you where it comes. Yeah, that's a great way to approach the question. Okay, I'm going to wait 1 more minute for questions. Otherwise, I will stop recording.
Hey.
Hey, Vinayak, go ahead.
Hi, is my voice clear, by the way?
It's audible, yeah.
Okay, great. So I just had a question on Irvin's question on the eigenvalue, on the time complexity of eigenvalue decomposition. Because like, how will you estimate that? Because you generally find an n-degree polynomial and then you find the roots of it. And then, you plug those back in to find the eigenvectors, and then you like standardize them, make them unit vectors. And then you find the final eigenvalue decomposition. But how will you like find the time complexity of it? Because you have a step where you have to numerically compute the roots of the n-degree polynomial, and that like might require a computational method like Newton's Raphson method, something like that. So like, how do you like find a proper neat answer in terms of time complexity?
So I think this question came up in a different sense before. If just to clarify, like this is not the same question. What I was asking earlier was the difference in time complexities when you multiply a matrix by itself n times versus if you have the eigendecomposition and then you go about this multiplication. What you asked is a valid question. The reason I don't think it is critical to know that is because once you decompose a matrix, it amortizes, right? Then you don't have to decompose it again and again. Like once you have a decomposition, you're good. So in that sense, like if you're doing some repetitive computations, and this is not answering your question, but this is giving you intuition for why I think it's not as important. But I will try. I don't have the answer. I will say I don't have the answer to your question because I don't know the stepwise considerations for eigendecomposition. Okay.
I think it's n square log n because for the roots finding we have fast Fourier transform. We can find the roots of an n-degree polynomial in n log n.
I would buy that. I don't know if I'm correct or not, but I would buy that.
I think that is true. I think because if we do without the normal multiplication, will take us n power 4, right? Because n cube for one matrix and n matrices. So I think so we are reducing an n square factor.
Fair. I think this is an important discussion to have, but probably on campus wire. Like, I don't think this discussion should end, but like probably make a post on campus wire, and I'll probably respond. I will respond to that with, oh, nice. That's useful. The internet. Sorry, I'm not sharing my screen, but yeah, Jay posted a link in chat. That's what I was looking at. Also note that this was 10 years, 1 month ago. So the field might have moved forward since, but I mean, it's eigendecomposition. So again, cool. Okay. So with that, I'm going to close the questions unless someone has burning questions, which they should be able to easily post on Campus Wire. We will monitor all of the places in general, like Discord, Campus Wire. Google Groups is mainly created to avoid, like, if there is ever an urgent email to be sent out, then to avoid your email. I should stop recording. Okay, thank you everyone for attending that lecture. I will stop recording now.